Generally, we all know what the word infinity means, something that is endless. But of course, what exactly is endless, and can anything really be it? Even as a child, we faintly understand the concept of infinity. When we competed over who had the most of something, we might have said that we have infinity of it, thinking that we trumped all possible higher numbers. That is, until someone else might have said that they have infinity plus 1. Then we might have quick-wittedly said that we have infinity times infinity. As children, this is a playful, meaningless game, and we mostly know it at the time. We know that you can't have anything bigger than infinity. But the irony is, you technically can. You can't actually add 1 to infinity or times infinity by infinity and end up with a bigger infinity. Infinity isn't even a number. It's a concept. It's a quality of a quantity and a set. A quantity so large that it can't be conceived or measured because it lacks an endpoint that would allow for a conclusive value. However, despite this, we do have some understanding of how infinity works and how some infinities are different than others. Despite how confusing it might sound, there are in fact as many even numbers as there are all the whole numbers. There is also the same amount of negative numbers as there are all of the integers including both all the positives and all the negatives. There are also as many prime numbers, 2, 3, 5, and so on, as all the evens, odds, negatives, and positives put together. This phenomenon continues to work in a variety of applications as a result of the concept of infinity. In order to understand how, it's important to understand at least a couple other general terms and concepts. First, number sets are considered to be the same size when a 1-to-1 correlation can be made between all the elements in both sets. For example, if you had a room with exactly 8 chairs, and in each chair there was 1 person, both the set of chairs and the set of people would be the same size. You would know this to be true even without needing to count them. For the number of chairs and the number of people to be equal, you would just have to know that everyone is in a chair and there are no more chairs. Order doesn't necessarily matter. Secondly, it is also important to note that a number set is considered countable only so long as every number within it can be listed if the lister had an infinite amount of time to do so. Of course, no one has an infinite amount of time, but theoretically and mathematically, it just has to be possible if someone did. And so, since there is an infinite number of countable natural numbers, 1, 2, 3, and so on, and there's also an infinite amount of countable integers, -3, -2, -1, 0, 1, 2, 3, and so on, by lining them all up side by side in what is called a bijection, you create 2 number sets that, although the numbers themselves don't match, their cardinality or quantity of elements in their sets do line up 1-to-1 forever. The same relative function applies to the infinite amount of even numbers, prime numbers, and so on throughout all of the rational numbers. The intuitive assumption that there must be twice as many natural numbers, which include both evens and odds, as opposed to just the evens or just the odds, is completely fair, but incorrect. All countable infinite sets are exactly the same size, no matter what they are made of. To help illustrate this and the increasingly nonsensical yet mathematically possible nature of infinity, a German mathematician of the 19th and 20th century by the name of David Hilbert created a thought experiment known as Hilbert's infinite hotel paradox, in which Hilbert describes a hotel that fits an infinite amount of people in an infinite number of rooms, each room being numbered in standard order with the natural numbers, starting at room number 1, then 2, 3, and so on into forever. One night, when the hotel is completely full, a man walks in looking for a room. Even though there is already a person in every one of the infinite rooms, the hotel manager accommodates the new guest by simply moving every current guest to the next room over. Their room number, n to n plus 1. The guest in room 1 goes to room 2, the guest in room 2 goes to 3, and so on. Since there is an infinite number of rooms, there is no issue. And so, infinity plus 1, or any finite number, equals the same infinity. That one might seem obvious. However, if that same night, a bus came that had a countably infinite amount of more people looking to stay at the hotel, Hilbert also showed that even here, there would still be room to fit everyone. By having all current guests move to the room 2 times their current room number, from n to 2n, all the infinitely many odd-numbered rooms would become empty, and thus, the infinite amount of new guests could be assigned to the infinite amount of available odd-numbered rooms, and everyone, new and current, would be allocated to a unique finite room number. A countable infinity plus another countable infinity equals the same infinity. Lastly, Hilbert showed that even if a countably infinite amount of more buses, each with a countably infinite amount more people pulled up, the hotel could still accommodate all current and new guests. The manager could do this a number of different ways, one being the utilization of the infinite amount of prime numbers. Since there are an infinite amount of countable prime numbers, the night manager could assign all current guests to a new room that is the first prime number, 2, raised to the power of their current room number. And so, the guest in room 1 would be moved to 2 raised to the first power, or room 2. The guest in room 2 would be moved to 2 raised to the second power, or room 4, and so on. Since each unique prime number raised to a different power produces a different whole number, the manager could then assign all the prime numbers following the number 2 to each bus, and each person within each bus would go to the room equal to their bus number raised to the power of their seat number. In other words, bus 1 would be assigned the next prime number, 3, the second bus would be assigned the third prime number, 5, and so on. And so, the person in seat 1 in the first bus would go to room 3 raised to the first power, or room number 3. In the second bus, the person in seat 3, for example, would go to room 5 raised to the third power, or room 125. This would continue on forever, fanning out every infinity into the infinite hotel with no overlap in any room. Every passenger on every bus will be assigned to a unique room with a finite number. Thus, even here, the same size infinity remains. Hilbert's hotel parable essentially demonstrates that all positive rational numbers are countable or listable and can always be mapped in a one-to-one correspondence with the infinite natural numbers. Thus, all countable infinite number sets are always the same size. Even if you add or multiply them all together, you would still end up with the same infinity. The hotel is always full and yet somehow always has room. However, infinity doesn't stop there. Georg Cantor, another German mathematician of the 19th and 20th century, slightly preceding David Hilbert, is regarded as one of the primary, if not the primary, leading figures in the realm of infinity. He helped create the foundation out of which Hilbert's hotel was built, but he also found a way to shut the hotel down. In the process of comparing different infinite sets, Cantor sought to find out whether or not there could be any infinities that don't fit. In other words, are there any number sets that aren't countable or listable, and therefore cannot be mapped in a one-to-one correspondence with the infinite natural numbers? All countable infinities and all conditions of the infinite hotel deal exclusively with rational numbers, which include the natural numbers, the negative integers, the fractions, etc. However, there aren't just rational numbers. There are all the real numbers, which are all the possible numbers that can be plotted on a number line, including all the numbers between each integer. This includes all rational numbers, but also all the irrational numbers, which are numbers like pi, the square root of 2, and so on. These numbers go on forever, infinitely within themselves with no repeating pattern. And here, Cantor discovered a different kind of infinity, an infinity that is too big to fit in the infinite hotel. Cantor discovered this through what is known as Cantor's diagonal argument, which demonstrates that if you were to create a list of all the real numbers, you could never complete the list, even in an infinite amount of time, because the list would still be missing numbers. He proved this by showing that if you change the nth digit of each number, as in the digit in the place that corresponds to the order the number is in the list, for example, the first digit in the first number on the list, the second digit in the second number on the list, and so on. You could do this infinitely over, and every time, a new number will be created that isn't already on the list. This is because the new number will be different than the first number in the first digit, the second number in the second digit, the third in the third, into infinity. As a result, you could never complete a list with all the real numbers, and thus, never create a one-to-one correspondence with the infinite natural numbers. This means that the infinity of real numbers between just 0 and 1 is incomprehensibly larger than the infinity of all the numbers on an infinite list of numbers. In this, Cantor discovered and proved that there are different types and different sizes of infinities. Now, some 130 or so years later, we still don't know how many, and we don't even know how much bigger the infinity of the reals is compared to the countable infinities. We just know that it's a lot bigger, even though they all go on infinitely. Some infinities, however, are apparently bigger than others. This of course warrants the question, are we wrong here? What does it mean when mathematic proofs don't fully line up, if at all, with physical reality, our sensibility, and logic? Is our sense wrong, or is our math wrong, or both? Math is often considered to be the language of the universe, and so, if something in math reveals a quality of reality that seems to exceed the limits of our comprehension, does that reveal something that nonetheless exists as a function of objective physical reality, despite our mind's inability to comprehend it? Or does it reveal that logic and mathematics are, at least to some degree, contrived or manipulated by the human mind, and at some point of extreme, fail when applied to actual reality? At bottom, arguably the concept of infinity reveals either our genius or our insanity. On one hand, if the universe has an end and consequently every object within it, then no thing and no one can ever truly exhibit or test or list infinity. And if nothing can ever test or count or exist infinitely, how can infinity exist at all? And if it can't, the mathematic concept of infinity would be a contradiction with physical reality, along with potentially other aspects of our mathematic understanding. But then, on the contrary, if the universe itself is infinite and either loops back around through itself again and again, over and over, or perhaps extends outward forever with no starting or end point, or perhaps something completely different that we can't even begin to fathom, in this case, in the case that infinity does exist, then so too would infinite possibilities. Our mere existence would thus be both product and parcel of infinity, like guests existing in one of the rooms of the infinite hotel of the universe, surrounded by every other finite possibility and condition of reality, plotted on a street of infinite other infinite hotels, all at the same time. And perhaps we get to stay in our room until we are shifted to the next in order to accommodate another infinity. Of course, since we can't know if infinity really exists and what exactly it might be, we can't know what infinity truly implicates in terms of time, existence, and the nature of the universe. It all remains as unclear as infinity itself. And perhaps to try to measure the infinite through finite reasoning, or to try to understand the irrational through a rational system of mathematic thinking, is impossible. It's not inconceivable, though, that a comprehensive understanding of infinity exists somewhere at some time in the future. As of now, however, all we can know is that infinity at least seems to poke at something. Some potential fringe of our current perception and understanding. An edge that we stand on and look out from, like an infant child standing atop a canyon's edge, looking out across a vast landscape that it doesn't yet understand or have the words for. We see something, but we don't know what it is. We are stuck in the dark of space with our numbers and no one but ourselves to translate them. If infinity does exist, though, there is quite literally an infinite number of possible scenarios in which we understand the infinite. Thanks so much for watching. New fine art prints are now available on the Pursuit of Wonder website. If you're interested in helping support the channel and would like to grab one, you can visit the shop at pursuitofwonder.com or by clicking the link in the description.